Okay, welcome to the Bytecode, where we look at smart contracts with the people who wrote them. I'm your host Shafu, and today's episode is with Lucas, who's going to walk us through the MakerDAO conduits. Lucas, thanks for taking the time, dude.
Thanks for having me. Today I'm going to walk us through two different conduits, which are part of the MakerDAO allocation system, which will be part of Endgame. I guess I can give you maybe like a link that you can put in the notes later, but I gave a presentation about what MakerDAO Endgame is and all the different components. This is going to be definitely way more technical, but that gives a good broad overview of what the allocation system will do and why we're doing this. But at a high level, just to give like an intro of what a conduit is, essentially what Maker is going to be moving towards in the future is having different sub DAOs have permissions to mint DAI and allocate them to different strategies. So this can be lending DAI into Spark so that we get decentralized collateral backing DAI, deploying into Coinbase custody to earn some yield with high liquidity, or deploying into RWAs. These are three, basic examples. We want to expand the offerings as much as possible, and this is what's exciting about conduits. Actually, that we're trying to introduce a lot more in hackathons is we want to encourage the community to come up with different ideas for conduits, different strategies for Maker to deploy DAI and earn a safe, steady, scalable yield in DeFi. So I'm going to go over two different conduits today that we have been working on. The first is going to be a conduit to deploy funds into Sparkland, and the second is going to be the RWA conduit. So Sparkland conduit, essentially how it works is you have an operator that calls deposit. So this is someone acting on behalf of the subDAO. And we have two central sort of registries in Maker that do lookups for ACL and for the appropriate buffer. What a buffer is basically it's just like a pot that holds DAI on behalf of a subDAO. The important thing though is that we pull DAI from the buffer into the conduit, supply that into Spark. Spark will then mint A tokens, and those will be held within the conduit. So you can think of a conduit as essentially like a position manager for multiple subDAOs to deploy funds into Spark. So if I look at this, we look at the data structure here. It's pretty straightforward. You have shares that are being tracked for each asset mapped to each ilk, which is the subDAO identifier that Maker uses, to the amount of shares that subDAO owns within the conduit. Because the thing is, the conduit's going to be holding an aggregated balance of A tokens for multiple assets for multiple subDAOs. So what this storage setup is doing is breaking that down so that we're tracking each subDAO's individual balance. And so you can see here you have shares and total shares, which is like very analogous to balance of and total supply in ERC20. Same idea, right? Yeah, this is the aggregate amount of shares for a given asset. Because the idea is this is built to deploy DAI, but we also want to be able to support potentially, USDC or different stable coins. We want to make this generic to support as many assets as we can. So this ilk auth modifier calls out to the roles contract. This is a very generic, highly configurable, centralized, central contract that basically says like, can this subDAO call this contract with this signature? And it's just like a lookup. So
Okay, Lucas, 1 second. Maker is famous for using weird terminology.
yeah,
You said ilk is a sub DAO ID, right?
Yes.
Okay,
So yeah, all it is a bytes 32 identifier
I
for
see.
us.
Okay.
You'll notice though that this conduit, and this is something that we want to kind of make known, is like conduits don't have to adhere to the maker terminology in the code, right? So we don't want that
Okay.
to be a barrier of entry for new participants, new developers. Like you can see here, right? Like I'm using pretty plain language in my
Th
deposit
yeah.
function.
Thank you.
Um,
Thank you,
so we
by the
want
way.
us to be as very approachable for new developers because I know that the maker terminology can be something to learn. So, um, but yeah, I'm gonna go over this relatively quickly because I want to get into the DSS conduits as well. But essentially, what this is doing, right, is you have a deposit function where you have a subDAO identifier, an asset, and an amount. We make sure that the sender is allowed to call this function on behalf of this subDAO. We make sure that the asset's been enabled by governance. And then we do a lookup to get the buffer for this ilk. And then we convert the amount to shares. And you can see here we're kind of using 4626 terminology. It's an internal function, but to make it feel familiar, because it's doing the same thing as what 4626 is doing essentially, converting the amount into shares using Spark's um, normalized income, which is essentially the exchange rate, effective exchange rate for converting between assets and shares in ray precision. So you're doing a ray div here, taking the amount, dividing by the exchange rate, and then you get the amount of shares. So since we're doing this atomically, we know that this will equal the amount that we're, and this has been, highly tested, but the amount that we're going to receive as the balance of I should say, sorry, the scaled balance of A tokens. Because the A tokens are continuously scaling. So the balance of returns the amount that's continuously accruing, but the scaled balance of is the constant underlying shares.
Okay. This is basically a 4626 with the difference. The main difference that I see is you using ilk instead of message.sender, right? I think from an interface point of view.
Well, from an yeah, essentially, yeah,
Okay.
because it is fulfilling the same purpose as a 4626. Really, it's like with additional logic, it's basically saying like, okay, we need to deposit some funds and we need to track value accrual. Except actually, it's a good, yeah, like we have get total deposits and get deposits, which are essentially convert to assets. So it's very similar, but it's not exactly the same. But yeah, it's a good call out. Um, so yeah, we take the shares for the asset and the ilk, we add new shares, same with total shares. So just tracking that state as we deposit. And then we're transferring the asset from the source into this contract, the amount. So we're taking, for example, DAI out of the buffer, pulling it into this contract, and then we're immediately turning around and supplying that into Spark. And then we receive the tokens after that's done. So that's a deposit. That's how that works. And then a withdrawal, pretty similar, but there is a little more logic here. So the max withdraw function, whoops, is, sorry, max withdraw is returning the minimum between an ilk's um, underlying assets for a given asset. So it's converting the shares, all of the shares that a given ilk has for a given asset, into um, the like underlying value. And then it's also taking the available liquidity in Sparkland and taking the minimum of those two values. So the minimum of those two values is the maximum amount that can be withdrawn by a given ilk for a given asset. So you're taking them, and these are two standard functions, by the way, for conduits. You got max deposit and max withdraw. So yeah, you're getting the amount, and then you're saying, okay, oh, and sorry, you're taking the minimum between the max withdraw and the max amount specified. So you're saying for this ilk, for this asset, this is the maximum amount that I want to withdraw. It might be less than that, but this is like the max that I want because it might get constrained. And we return the constrained amount here. So this function essentially tries to withdraw, as much as you can up to the specified amount. So you get the amount, and then you say, okay, what are my shares? And you're taking the minimum between the shares of that asset for that ilk, or the rounded shares for the amount. We're rounding up to be conservative here. And then you're reducing the shares in the state by this withdrawal shares. And this is important because it's important to round up here because we want to be, we want to be conservative when we're dealing with our own state to make sure that, there's no bad rounding, essentially. And then, we're getting our destination to send the funds back to, and then we're withdrawing the funds. So you can see it's basically the reverse in this situation, where we're calling withdraw from the pool, we're burning the A tokens that were held in the conduit, and then we're getting the underlying asset back, and then we're transferring that to the buffer. So that is like in a nutshell how conduits that atomically deploy funds into basically any conduit that deals with like direct DeFi protocols will be able to do this atomic deposit and withdraw, where they're deploying into like some yield bearing on-chain strategy and then withdrawing from it.
Okay, nice.
Does that all make sense?
Kind of makes sense.
Cool. I'll just do a quick little plug as well for we made our own safe ERC20 implementation. ERC20 helpers is this little repo that we made that just has like three things, like a mock ERC20, like a mintable ERC20, the ERC20 interface, and this safe ERC20 library, which is just like a very minimal implementation of the safe ERC20 library. So yeah, if people are curious to check this out, that's in our GitHub. I can give you a link too for that.
Yeah, for sure. Any specific reason why you guys re-implemented that?
I just don't like importing. Personally, I just don't like importing external dependencies that are bloated for what we need, and just have like a lot of code. Like this is implemented in like 70 lines. It's like very tight and like concentrated to what we want to do. So yeah, as long as it's not too complex, or we always have a discussion of whether or not it's worth doing. But that's something that I believe in is like, making the minimal possible implementation. We also implemented our own upgradable proxy, which is like, you can see here, it's like very small. And it has the maker standard rely deny syntax for tracking off, but it's just like a very tiny proxy.
Yeah, I hear that more often recently about external dependencies, and it's kind of a trade-off, because obviously when you write your own code, you need to re-audit that and stuff like that,
Yeah.
So yeah, it's interesting.
Well, it's like I was saying earlier, like it's a decision, right? Because we did audit both of these. but it was easy to audit because it was so small,
Mm.
right? Like it's like we can just throw another 70 line contract in this audit. It's not a huge undertaking. Um, but yeah.
Okay.
Awesome. All right, well that is the Spark conduit. I'm going to move on to the RWA conduit unless you have any other questions.
Let's do it.
All right. Oh, shoot. Okay. So this is a similar kind of contract in the way that it adheres to the same standard interface of a um, of a conduit. Whoops, sorry. Um, but it's a little more sophisticated because this conduit um, is dealing with real world asset implementation. So Maker has a pretty large real world asset, um, deployment currently. So what we're aiming to do is to move all of those real world asset um, deployments to use this structure, because by using smart contracts to track all these positions, all these fund requests, and all these returns, which I'll get into more later, it really improves the visibility of all of these funds moving and just adds a lot more rich, like on chain data for dashboards and this kind of stuff. Um, so, this is the initial implementation of this. As different use cases come up, as things get more solidified over time, we're going to, continuously iterate and improve on these things. Um, but yeah, this is the what's called the arranger conduit, and it's called the arranger conduit because it's using the arranger model that Maker uses for RWAs. And so the major difference between this and the Sparkland conduit is that you have funds getting deposited and held in the conduit, and the arranger, who is a trusted actor that is working on behalf of Maker to deploy funds into treasuries or whatever it might be, will pull the funds and deploy them. So it's a two-step process instead of a atomic deposit and immediately earn yield. You're depositing, and then the arranger can come in and see this aggregated pool of funds that multiple sub-DAOs have deposited, pull that out, and deploy it into a yield-bearing strategy. So the goals of
Hmm.
this are to be maximally simple for arrangers, because all that they want to do is come in and pull and deploy funds, um, and also fulfill all the needs of all of the sub-DAOs.
Okay. So the arranger is some sort of trusted third entity that acts on behalf of Maker, basically.
Yes, yeah, there's like, very hardened legal agreements and structures that are put in place that ensure that these entities are, behaving as expected.
Okay.
And yeah, that's essentially the model, is that they're pulling the funds and deploying them. Um, so, by the way, just this is something that us Solidity nerds Twitter battle over sometimes is section labels. So I'm going to
Oh.
take this moment to shill my style of section labels. 'Cause, I've been through like 5 different iterations of section labels, and I do think that this is the one for me. I love.
Okay.
So, because people try to center them sometimes, and they're always like slightly off center, I find, um,
Yeah,
or
that's true.
or they don't have a constant length, and they're centered. Like I did that. I used to do that. But my new final sort of, well, not final, but the latest is this version. So essentially, you can see here I have a line guide, and this is at
Mm.
100 characters. And so these are all constant lengths, and they're left justified. So they're always, they never look out of place. And you'll see, right, they act as like a little box. So everything within a section is contained, like nothing goes past the line of the section label.
Hmm.
You can see here all of the code is contained within the length of the section label.
Yeah.
So I don't know. I just find it really nice to be able to navigate code. Um, so yeah, there it is. All right, so yeah, the data structure here you can see is similar but more sophisticated than the Sparklands. So you got deposits, requested funds, withdrawable funds, and withdrawals. So deposits is a continuously increasing value. That's saying like what are the aggregate cumulative deposits for a given ilk for a given asset. Or sorry, this is the this is the total version. This is the balance of version. Um, so I'm just going to go over each one because now you know the balance of total supply analogy here. So you got the total deposits continuously accruing. You've got the requested funds, which is I'll go into in more detail, but essentially, in order for a subDAO to get funds back from the arranger, they have to request funds on chain so that the arranger knows, okay, they need $10 million. Let's return those funds now. They have to signal on chain. So this is the total requested funds that increases when they request and decreases when that request is fulfilled.
Hmm.
And then you've got withdrawable funds. So this increases when the funds are returned and then decreases when they're withdrawn. So when funds are returned for a subDAO after they request, they're withdrawable, and then they withdraw them. That goes down. And then this is total withdrawals, which is similar to total deposits, just a continuously increasing cumulative withdrawal amount. So deposit is pretty, similar and to the last conduit. So you got your deposits, you're looking up your buffer, and then you're pulling funds into the contract for the buffer. So that's all that this is doing, just pulling DAI, for example, into the conduit and holding it there and tracking the individual subDAO's position amongst the aggregate balance of DAI. And then you've got, I'll just go in kind of the order of operations for these actually. So then you got draw funds, which is the arranger is coming in and saying, okay, I want to take this amount, or sorry, this asset, I want to send it to this destination, and this is the amount. So I'm going to make sure that the amount is less than the available funds. And this is really important. So the available funds here is the aggregate balance of that asset minus the total withdrawable funds for that asset. Because you have an encumbered portion of the balance that's earmarked for withdrawals for a subDAO. So if you have $10 million of a balance, but you have $2 million that you've returned for a given subDAO to withdraw, you can only draw 8 million to deploy. You can't withdraw 10 million because you're dipping into the withdrawable funds of that subDAO. So that's what available funds is doing here, is it's making sure that the arranger can only deploy the funds that they should be able to deploy, essentially. So that's really important. And then, yeah, we have a broker allow list for the destination and the asset. We just make sure that they're a valid destination to send these funds to. And then we just do a transfer. And you'll notice here that there is no state that gets updated when this happens. And the reason for that, we kind of tried to figure this out, but the reason that you can't really decrement a given subDAO's deposits is because this is drawing on the aggregated balance of the whole conduit. So you don't actually know per se which funds belong to who, unless you wanted to do a more elaborate data scheme. But we figured that it wasn't actually necessary to do that. Like you could loop through and do something like that, but it wasn't actually needed in the end. So that's why there's no state updates here.
Okay, it's pooled in, and you don't have the information which amount belongs to which sub-DAO or something.
Yeah, but you do have the information of like the relevant information, which is like the sub-DAO's deposits that they've put in,
Hmm.
and then the amount that they've like what we actually care about at the end of the day is how much a sub-DAO's put in, how much they've requested, and how much they've been able to withdraw. And then from that, we can do all of the financial calculations that we need. Again, we want to move towards more like, on-chain RWA strategies so we can have even richer data sets. But this is where we're starting with. And yeah, this allows for maximum flexibility for all RWA implementations currently.
Yeah.
So you draw the funds, and then the next step is you request the funds. So fund request, you push to the fund request array, and it's essentially just this struct that says, I've requested this amount, I don't have any filled yet, and this is an arbitrary string for the info that you can pass along, which is like essentially predefined um, information that you can convey to an arranger as a sub-DAO, according to like legal agreements that you can say, because for example, right, like who knows, maybe you want to liquidate $10 million, but you have um, a pretty relaxed time preference, so you're okay if it takes like 2 days, for example, um, or because you want to maximize the yield, or you have like a very, you know, uh, quick time preference where you need the funds right now, and so you would request that, and you would get some slippage probably because you have to liquidate very fast, but that's okay. You just prefer the funds earlier, so you can convey this very arbitrary, flexible information through this string. Um, so this is all emitted on chain so that the arranger has all the information they need. And then you can cancel fund requests. I won't go into this too much. You just can cancel it if you're a sub DAO that didn't want to actually go through with that fund request. You can remove it. And then here is the next one, which is you can return the funds. And essentially, you this is a quick thing I'll just go over is like the funds are going to be sent from a different location than the arranger is going to be calling the funds from. So we're using a push pattern here. So funds will be sent into the contract, and then return funds is called to change the state to correspond to the balance update. So for a brief period of time, available funds increases, but then it decreases because the withdrawable funds increases to catch up to that amount. So your withdrawable funds and total withdrawable funds increases. Your requested funds and your total requested funds goes down by the amount requested. This is key because if you request, like, I don't know, if you request $1 million and you get 1.2 million, then your requested funds should go down by a million. And if you get 800,000, it still goes down by a million. So it's actually the state update for the requested funds, regardless of what happens, is always removed by the full amount of the request, not by the
Hmm.
resulting returned funds. Um, and then the withdrawable funds is increased by the amount that was returned, because that's the amount that's actually available for the sub-DAO to withdraw. And so, yeah, we wanted to make this maximally flexible to, adhere to any situation that might arise. So you can return less than was requested or more than was requested as an
Hmm.
arranger, depending on the situation. And we'll deal with that data accordingly. And no matter what, it's a one-to-one return. So if you return funds, that fund request is like completed and removed, no matter what
Yeah,
happens.
Lucas, why would you return more than requested?
Um, if if there was yield that has accrued since the request was made, is like
Mhm.
a quick example. There's different situations that could happen, but that's like one of them.
Okay.
And yeah, that's just what we wanted to be able to handle. Um, so and then yeah, you got the events here, and then the last thing is the withdrawal. And so the withdrawal, pretty straightforward. You're reducing the withdrawable funds. You're adding to the withdrawals, the cumulative withdrawals, and then you are sending the funds to the buffer. So that's like a complete, cycle of depositing, drawing funds, deploying the yield strategy, requesting funds, getting the funds returned, and then withdrawing.
Nice.
So this was all a really necessary preamble to the tests because I want to get into some like variants and stuff like that. So it's important to understand also just generally, but I think it's going to be a lot more meaningful to go over these tests now with this knowledge.
Yeah, let's do
So
it. But I have one question.
yeah.
The file pattern, I think, is interesting on line 69.
Oh yeah, this is a standard maker approach.
Yeah, Maker introduced that, right?
Yeah. I
Yeah,
I
okay.
like it. It's you know, it's essentially like a setter that can just handle setting any value based on the keys.
Mm.
So you just have one file function and all your settables, and then you have it like keyed on what you want to set. So if I want to set the arranger value, I'll just put in an arranger key and the value rather than calling set arranger as a separate function.
Mm.
It's just like a nice tight way to set everything. So it's nice. I like it.
Cool. Yeah, let's jump into the invariance testing.
Awesome. Okay. So yeah, I mean the files just actually really quickly before we do that, I got like these are all the unit tests, which we can go through, but I think, so actually some things that I would like to say that probably haven't been gone over in different podcasts is like one testing pattern that I really like is to test the boundaries of conditions and label it as boundary. So an insufficient approve for a deposit, what you're doing is you're minting the appropriate amount of assets and you're approving 99 instead of 100. And then you're asserting that you're getting an arithmetic error in the ERC20.
Mm.
And then you're actually approving the correct amount. And then you're asserting that it works correctly.
Okay.
So for any condition, like I feel like return funds boundary. Yeah, like the available funds, like checking the available funds conditions, right? Um, like if I'm depositing and then I request funds, I'm just trying to figure out, sorry, how this worked again. So yeah, if there's like 39 available funds here, and then I return 40, um, it'll revert because of that condition that
Mm.
only allows you to return at at most the available funds, and then I just mint one more way into the contract, so the available funds goes up by one and is 40, and then I return the funds. So for um, any requires that you have in your contract that are like greater than equal to or greater than or less than whatever, if you have any of those or any basically anything that will revert based on like amounts, I find it's very useful to test like within one unit. So you
Mm.
can test the exact point that it failed, and be certain that it's like, because it also exposes, right? Like if you have like a less than condition when you should have a less than equal to condition,
Yeah.
like you'll know right away, oh shit, that didn't fail when I wanted it to. And then you realize. So big fan of boundary condition testing. And I think that it's a good practice. So yeah, ton of unit testing as always. Make sure to unit test a bunch, and then you've got one another thing that I wanted to say is like uh, personally, I find that having expect emit on every call in a test kind of ends up cluttering a lot of
Mm.
what you care about. Um, so what I've done in this repo is made a dedicated file that basically says like for this cancel fund request, like am I getting what I care about, and is it changing based on what I expect it to change on? So you can do like if you have branch logic that would affect the values emitted in your events, you would want to test that within this context. Um,
Okay,
but it's
interesting.
yeah, it's
S-
nice because like for example, right, like my deposit tests, like they're just performing deposits.
Mm.
So it's
Yeah, I
nice,
like that.
clean, and tight.
Yeah, that's nice.
Yeah. Also, I want to mention I learned this from Maker, and I'm a huge shield for it. Is just alignment in general. So aligning, especially specifically for assertions,
Mm.
aligning the two sides of an assertion makes it very easy to audit and review code. So you'll see if I have a multi-ilk deposit here, like I'm minting into two buffers and then I'm checking all the balances and then all the state, and then I'm depositing and then I'm checking the balances and the state again. And you can see it tells a story that the funds are moving from buffer 100 into the conduit, and the deposits have increased by 100 and the total deposits have increased by 100. So it's very easy to
Yeah.
see the before and after state and compare the values and like just understand like I always view tests as like telling a story or conveying information about how logic should work to like an auditor or a PR reviewer. So I always try and make my tests as like clean and easy to understand as possible because the easier it is to understand, the easier it is to find an issue.
Nice.
Um, so
Yeah, I do that too, Lucas. We nearly have the same code style taste,
nice, good.
except for the section comments.
Yeah, dude.
I don't do section comments.
Oh, you don't do them at all.
No, I don't do them.
True, true. Um, cool. All right. So yeah, now we will get into invariance. So invariance was fun for this contract in particular because there was a lot of opportunity to do invariance. So I like to. Where should I start here? I'm gonna start with the handlers. So I'm gonna assume the audience has like some base in invariance. I won't go too deep into the like underlying structure. I'll kind of just go into how it works. And hopefully that will also just paint a picture of the underlying anyways. So we've got um, essentially three handlers. We have a handler base, but we have three handlers. So we have an arranger who is going to be drawing our funds. We've got a operator who's going to be depositing, withdrawing, canceling. And we've got a transfer who's just going to be transferring funds into the contract. Um, and to try and mess with invariance, right? As an invariant developer, you want to try and figure out ways like how can I make things break? And
Mm.
that's in your handler design, you want to try and figure out ways like, okay, if I have, because if no one transfers any funds into the contract, all the invariants are very tight and clean and it's very
Mm.
easy. But as soon as you start transferring, it gets a little harder. So that was one thing. So in my handler base, I have a bunch of functions that are essentially like helpers. So I've got like all my active fund request IDs. This is where you throw logic that you don't want to put in your actual smart contract. That's like very gas intensive, very inefficient, but also very useful if you need them. They're just kind of like helpers. So get active fund request IDs for an ilk, whatever. You can get the asset. These are interesting. So um, in the test contract, we specify the number of assets and the number of ilks. You could load this from environment variables too if you wanted to get fancy.
Mm.
But what this does is in the configure the initial setup, um, you are creating assets and ilks and brokers, and you're pushing them to an array. And so that you have multiple assets, multiple ilks in the system, and you choose them at random. So you wanna set up your system so that you have like a somewhat complex kind of situation going on. So you want to make sure that you have multiple sub DAOs, depositing or withdrawing multiple different assets, and you're trying to make the situation as complicated and the storage set up to be as complicated as you can to try and reveal you know, any assumptions that you might have made that are wrong or whatever it might be. That's what invariants are very useful for. So, and then you've got your configure handlers function that's just like setting up the roles, just kind of doing the setup that you want to do. And then you've got your invariant assertions. But before I go into this, I just want to quickly say like this is like a nice pattern. Is like if you want to get a random asset, get a random broker, get a random ilk, you hash a seed that you pass into this function, just like a random value, and get the uint256 of that, and then you use a modulo, and then you do that over the length, and then you basically get an asset at a random index in the array. So it's a nice little thing to do to pick random values in the arrays. So, and then it's another getter here. So when making invariants, I try and think of, the base cases that I want to cover, and then try and like get a little more creative. So, and another thing that I do is you'll typically run into situations where you're doing an invariant for multiple, like you can see here, multiple assets and multiple ilks. You're iterating and aggregating. And so that is a very expensive operation because you're running this assertion after each call in an invariant campaign, right? So the more intensive these calculations are, the less efficient it is. So what I like to do is to combine invariants into like one function. If I'm doing like a big loop, I might as well just like calculate everything that I need in this invariant. So here I'm summing all of the deposits, requested funds, withdrawable funds, and withdrawals. So this is basically like a sum balance of equals total supply invariant, but for all of these state variables. So I know that for all of the assets, the sum of all of the ilk's individual state variables equals the assets aggregated value. So yeah, that's the first invariant. The second one is a pretty quick one, but this is like something that I believe is like you should just almost make invariants to the point of feeling redundant because they're like the more you have, the better. So like one of them here is like the balance should always be greater than the total withdrawable funds, no matter what, right?
Yeah.
So that might seem kind of like obvious or like, you know what I mean? But it's important to put it there anyways, because who knows? Maybe there is a situation where this becomes not true, and then you need to investigate why. And then we're gonna get a little more creative down here. So so this is a ghost variable here, returned funds. This is not in the smart contract.
Okay.
This is in the handler. And so what the handler is doing in the arranger is it's tracking aggregated drawn funds and aggregated return funds. So for each time that a arranger is drawing funds, we're tracking that happening in the state of the arranger handler. And then we're doing that as well for return funds. And so I'll go into why this matters in a second, but it's important. Like for each call that you're doing this for, you're tracking the corresponding ghost variable. So why that's important is you're saying, okay, for this asset, I'm going to make sure for all assets, for each asset, I'm going to say, okay, the withdrawable funds has to equal the total return funds minus the total withdrawals. So if you have funds that have been returned but have not been withdrawn, then they should be withdrawable. And that should be exact. Because the only way to not, well, there is no way to not do that because the state in the contract is only updated by those functions. There's no external factors that can change that. There's no like balance changes that can affect this from being true in theory. So that's what you want to test is you want to say, okay, my withdrawable funds should be the total amount of return funds minus the total amount of withdrawals in aggregate. And then this one's my favorite. So you've got your arranger handler and your transfer handler. Your transfer handler, this guy is just transferring funds into the contract repeatedly. But we're also tracking the amount that's been transferred into the contract. So we know how much has been transferred. So what I'm calculating here is the net balance of the contract. So we're saying, okay, for this asset, what is the total amount that's been deposited? What is the total amount that's been returned by the arranger? What's the total amount that's been transferred into the contract? Minus the total amount that's been drawn from the arranger and withdrawn by operators. So it's basically all of the inflows minus all the outflows.
Mm.
That is your net balance. And then you can just check, okay, is my balance equal to what it should be? And if that's true, it feels good because you know, okay, all of the inflows, all of the outflows is always equal to the current balance. So your state is being tracked the way that you expect it to be tracked. So that is that one. And then you've got checking that the balance is equal to the available funds plus the total withdrawable funds. And this one seems a little bit redundant because available funds is balance of minus total withdrawable funds in the contract. But this is just kind of a check to be like, is that actually happening? Just another place to check it. So we've got all of this, and so something that I think is kind of nice to do is I have bounded invariants. So if I run like forge t, I'll get all my invariants to run. And you'll see that there's 0 reverts. And the reason for that is because I've designed all of the handlers, the bounded handlers, to work in such a way that they never revert. So for example, if I'm drawing funds as a bounded arranger handler, I am preemptively bounding the amount that I want to draw by the available funds. So that I ensure that every call that I'm making as this handler is going to be successful. And the reason that I like this pattern is because if you can get to the end of an invariant campaign with zero reverts, you know that everything is working exactly as you expect it, and that the contract itself is not reverting in a situation that you don't expect. Because that's also important, is you don't want to be in a situation where you're getting reverts and you don't know why. Um, because who knows, maybe that's like a result of locked funds or something really bad. So I highly recommend using bounded invariants as well as unbounded invariants. And what unbounded invariants are is, you'll see I've got this bounded that's calling super. So basically all the logic to call the function and track any ghost variables is in this inherited base handler where you're, you know, drawing the funds, doing whatever you need, but you're doing it with a completely unbounded amount. So who knows? Maybe there's like $100 in the contract and you're trying to withdraw 10 million because that's the
Mm.
fullest value. Like, it's going to revert, but that's fine for this. But it's not fine for this. So you want to bound this value to be $100 if it's greater than that. So what I do is I'll run bounded invariants by default locally, but in CI, I will run unbounded invariants as
Mm.
well. So if I copy this command and run it down here, you'll see it's taking a while. One sec. There you go. So you see like a bunch of reverts. Almost half of the
Mm.
calls are reverting. But this is also important because who knows? Maybe you've introduced some logic in your bounded handler that reflects your assumptions about how the protocol works.
Yeah.
And then when you do an unbounded call, maybe a bunch of them revert, but maybe one of them actually violates an invariant,
Yeah,
right?
you could make an error when writing the bounding logic. Just
Yes. Yeah.
mm.
And so it's really important to have both. Like, I'm a huge believer in bounded invariants generally, but I think that unbounded invariants are extremely important to have as well because they can reveal um, something that you might have not have thought of before.
Mm.
Um, so they can violate an invariant potentially that you didn't realize there was like a way to do that. Um, so yeah, that's pretty much it for the testing. Um, yeah, there's harnesses that we use. That's pretty standard for you guys, I think. The rest is honestly pretty like straightforward. I think I'm just a big believer in keeping things really tidy. Oh, another thing that I recommend doing actually is just making a general assert invariance function in your unit tests that you can just throw everywhere, you know? So like my deposit contract will just like assert invariance um,
Mm.
at each step of a unit test. It's an easy way to start asserting invariance early on in the development cycle without having to set up this like extravagant, invariant test suite. You can just quickly start like making sure that things are working the way that you expect within your, nice tidy unit tests. It's one step, but I would say it's very important to continue to do invariance before going to like production, because that would be when you discover things that you hadn't really thought of before.
Mm.
Yeah. And so yeah, this both of these repos have been through multiple audits, Chain Security and Spearbit. Um, what we're looking forward to doing now is getting the entire broad system deployed and starting to do forked integration testing,
Mm.
as well as Certora testing, to make sure that these contracts are as hardened as possible. Um, So yeah, that's pretty much it.
Nice, dude. Yeah, thank you for your presentation, dude. This was really interesting.
It was fun.
If people want to reach you, probably Twitter, best place, GitHub.
Yeah, I think Twitter is a good spot. So Lucas Manuel underscore ETH. We can maybe add it in the link too.
Yeah,
Um, and then yeah, my GitHub is Lucas Manuel. Um, and yeah, just DM me if you ever want to learn more, or just tweet at me, whatever. And yeah,
nice. So I'm gonna link Lucas' Twitter, GitHub, the link to the repository in the description below. Lucas, thanks again for taking the time, dude. And yeah, guys, see you in the next one. Bye bye.
awesome.
Bye bye.
Thanks, guys. Bye.